In the previous video, we talked about using Cramer's rule to solve systems of equations and realized that it's only really practical for systems maybe up to order 3 or possibly 4. So what we want to do now is solve larger systems, and to do that we're going to use what's called Gaussian elimination, and we're going to use the naive form. Again, we're trying to solve a system of linear equations, so for consistency we have the same exact 3 equations and 3 unknowns, and what we're going to do now is use naive Gaussian elimination. So Gaussian elimination is just a specific form of elimination of variables, which many of you have already encountered, and so there's 2 parts. The first part is forward elimination, and then we go to part 2, which is backward substitution. And during forward elimination we're using elementary row operations. And elementary row operations let us modify a system of linear equations without changing the system itself. And the 3 options that we have are to switch rows, so we can make one equation, maybe equation 1, we can change that to equation 2, and equation 2 can become equation 1. We haven't changed the system at all, and we haven't even modified the equations, we've just reordered them. Then there's row multiplication by a non-zero factor, so we can multiply both sides of one equation by some constant as long as it's not 0. And then the third, we can take 2 separate equations and add them together or subtract them to yield a new equation that we can then replace one of those 2 with. So we can add equations together to get a new equation. So for forward elimination, the goal is to take our original system here and take this original coefficient matrix and convert it to an upper triangular matrix. Now if we look at this upper triangular matrix, specifically the last equation, what we have is one coefficient in terms of one unknown here. So what we have is a33 times x3 equals b3. And when we get down to only one unknown in an equation, we can start solving for the unknowns and then move on to the next part, which we'll talk about here. So there are 2 general forms. The word version here says that our new equation is going to be equal to the old equation minus some factor times what we're calling a pivot equation. Now these take care of or use these 2 elementary row operations, the multiplication by a non-zero factor as well as the addition or subtraction. So we take the old equation that we're modifying and subtract a factor times the pivot equation to get a new equation. Now the whole goal is to eliminate coefficients systematically so that you're left with an upper triangular matrix. The general form in terms of element by element is written here, and we'll take a look at this in a little bit, but it's the exact same thing as the equation on the left over here. So once we have our upper triangular matrix, we're going to start with the last equation and solve for our unknowns. So if we look at this 3 by 3 system, we only have one unknown in the last equation, so we would solve for x3. And then once we know x3, we can go to equation 2 and use that x3 to solve for x2, since x2 would be the only unknown. And then finally we could use x2 and x3 in equation 1 to solve for x1. The general forms listed here, so xi is equal to the right hand side minus the sum of the coefficients times the variables we know, and then we're going to take that whole sum or difference and divide by the coefficient. Now we start at the bottom n and we work our way back up to equation 1 with a step of -1. So looking at an example here, we have the same system and we're going to be using the general form of forward elimination. So first we're going to do this using the word form. So we're going to do it one equation at a time rather than element by element. So to start, we use the pivot row at the top, and once an equation is the pivot row, you do not modify that equation ever again. So that is in the final upper triangular system. So we're going to start with a pivot row equal to 1, and we're going to use equation 1 in our pivot row spot. So if you remember, the equation is old minus factor times pivot equation equals the new. And the goal is to modify equation 2 but get rid of our x1 coefficient. So we'll lay these out. We have our old equation, which is equation 2, minus some factor times our pivot row. And the factor comes from the coefficient you're trying to eliminate divided by your pivot equation coefficient. Now the coefficient on the diagonal of your pivot row is known as the pivot element, and that can be referred to as AII if I is your pivot row. When we're trying to eliminate the coefficient for equation 2, the factor would be 1 over 4. So if we multiply 1 over 4 by our pivot row, we have this modified equation. And then we're going to take the old equation minus our modified pivot row equation to get our new equation. So now this new equation 2 doesn't have an x1 term, it only has an x2 and an x3. So we would replace our old equation, equation 2, with our new equation 2 that only has the two unknowns. Looking at this in a slightly different form, let's look at the element by element general form. So here we still have pivot row equal to 1 and our pivot element is 4, and we're trying to eliminate this coefficient, the x1 coefficient for equation 2. So for the general form here, let's let I equal 1. We're working to modify row 2, so j equals 2. And then k is the columns, and we're going to go through all of the columns. So k equals I to n, so 1 to 3. So first let's compute our factor. So again, it's the coefficient you're trying to eliminate over the pivot element. So our factor is 1 over 4. And then we're going to proceed for k equals 1 to 3. So first we let k equal 1, and we say that a21 equals a21 minus our factor times a11. So looking up at the matrix, it's this new value is the old minus our factor times the corresponding element in our pivot equation. For a22, it's the old value of a22 minus our factor times the corresponding element in our pivot equation. So it's negative 2 minus 1 over 4 times 2. So that gives you negative 2.5. a23 would be 5 minus 1 over 4 times 3. And then lastly, since we did this to the left-hand side, we have to do it to the right-hand side. So b2 is equal to 2 minus 1 over 4 times 1. And this gives us the same exact equation 2. So continuing just using this general written equation form, doing this equation by equation instead of element by element, we would be eliminating the x1 coefficient for equation 3. So we have equation 3 minus our factor times our pivot row. So our factor is negative 2 over 4. And if we modify the pivot equation, this is the equation we have. And when we subtract the modified pivot equation, we end up with 0x1. And we actually end up with 0x2 plus 3.5x3 equals 3.5. Now this becomes our new equation 3. Now even though we have a 0 here, let's continue as if we don't, because you do the same process every single time for Gaussian elimination. So we would change our pivot row to pivot row 2, and now we're going to use the pivot element a22, which is negative 2.5, and our goal is to eliminate this coefficient. So we're going to create a new equation 3 by taking the old equation 3, subtracting some factor times our pivot row. So our factor is the coefficient you're trying to eliminate over your pivot element. So our factor here is 0 over negative 2.5. So when we multiply that factor by our pivot equation, we actually get all zeros. So we take our old equation minus our modified pivot row, and we get our new equation 3, which only has an x3 coefficient. At this point, we've achieved our goals, so we have taken the original system and converted it into an upper triangular system using only elementary row operations, which could subsequently be reversed if we wanted to go back to the original system. We'll move ahead with backward substitution. So we're going to use the last equation to find our last unknown. So if we write out the general form here, it's really only going to be 3.5 divided by 3.5. But let's take a look. Here's equation 3. The general form says xi equals bi minus the sum for k equals I plus 1 to n of aik xk, all divided by aii. So we have I equals 3, so x3 equals b3 minus the sum from k equals 4 to 3 of these products divided by a33. Now looking at the sum, we're summing from 4 to 3. So in a summation you increment by 1, and since 4 is already greater than 3, the summation is actually 0. There are no terms in the summation. So we are left with 3.5 divided by 3.5, which gives you an x3 equal to 1. Now we take that value of x3, and we know that, and we work back up and go to equation 2. So now we're going to use equation 2, which is negative 2.5 x2 plus 4.25 x3 equals 1.75. So the general form says take everything you know, move it to the right hand side, and then divide by the coefficient. So we have x2 equals b2 minus the sum for k equals 3 to 3 of a2k xk over a22. So there's one summation term here, which turns out to be a23 times x3. So when we do this, we get 1.75 minus 4.25 times x3, which is 1, all divided by our coefficient here, negative 2.5. And x2 turns out to be 1. And now that you know x2 and x3, we're going to use equation 1 to find x1. So we have 4x1 plus 2x2 plus 3x3 equals 1. And again, we're going to take everything we know from the left hand side and move it to the right, and then divide by our coefficient. So the summation terms end up being this 2x2 plus 3x3. But let's take a look. So I equals 1, we end up with b1 minus the sum for k equals 2 to 3 of a1k xk, all divided by a11. So b1 minus a12 x2 plus a13 x3, all divided by a11. So again, as we said before, we're just taking these terms, moving them to the right, and then dividing by this factor. So if you do that and plug in the numbers, you end up with x1 equal to negative 1. And so we started with our upper triangular matrix that was the end result of forward elimination, and we did backward substitution, and we found all the coefficients. So our solution vector here is negative 1, 1, and 1, which is exactly the same thing we got using Cramer's rule. However, this is much more efficient for systems larger than about 3 equations and 3 unknowns, which are pretty common in engineering practice.